Okay, so we're talking about individual differences in color perception, and we're looking at, the question of, whether or not everybody sees colors in the same way. Previous study that topic we were talking about, study by Lindsay and Brown from 2004, saying that people can basically agree on 11 colors. So let's look at, whether or not people see colors in the same way when we're talking about color deficiencies, because there is a portion of the population, about 8% of the male population and about 0.5% of the female population that has some form of color blindness. So color blindness is problems with the ability to discriminate those wavelengths. So remember that we need to have 3 cones to be able to discriminate colors, because we have to because our brains rely on the relative activity of 3 cones for cases where there's some ambiguity in the responses of the cones to 2 different wavelengths. So we need to have those 3 types of cones so we can use the relative activity of all 3 to discriminate the colors. So people with color deficiencies will be missing 1 cone. So people that don't have 3 cones have difficulty distinguishing between colors. So these people are often referred to as being color anomalous. It's a term for color blindness, because most people who are considered colorblind can still discriminate some colors based on wavelength, but they are limited, and there is some of the spectrum that they don't have access to. So let's look. So first we've got trichromats. That is what we've been talking about. So this is, people who have 3 cones and can discriminate among more wavelengths across that spectrum. So one form of color blindness is called dichromacy. So dichromats, they have 2 types of pigments. So they can see colors, but they can't distinguish all colors. And there's a few different types of dichromacy that can happen depending on which cones are kind of missing. So deuteranopy, that is caused by an absence of medium wavelength cones, so those ones of the greenish variety. Protanopy, that is an absence of those longer wavelength red-ish cones. And titranopy, an absence of those S cones. So that is the more rare. Titranopy is the more rare. So let's look at what part of the spectrum we have access to for people with only 2 types of pigments. Okay, so protanopes. Okay, so let's look at this figure. Okay, so this is the regular spectrum that people with normal trichromacy would have. So let's look here. So deuteranopes, this one over here. You can see, because they are missing those medium wavelength cones, so they're missing kind of this chunk of the spectrum right here. So this is kind of what they would see. So titranopy, on the other hand, this one down here, you can see that they are missing. So they are missing. They have problems with the blue-yellow hue discrimination. So they are missing those S cones. So they have difficulty the blues and yellows. And so people who are truly colorblind would have monochromacy, which would be this one over here, which that is truly color. These people are truly colorblind. People that don't, that have just one type of pigment. So people who have monochromacy, they don't have just rods. They have rods and one type of pigment. But of course, with one type of pigment, that just doesn't give us enough information to discriminate any colors. So they do see in shades of gray. So that's what we were just talking about, monochromats. They have just one type of pigment. They see shades of gray. These are people who are truly colorblind, whereas the other forms of color blindness, where they are missing just one type of cone, there's parts of the spectrum that they can't discriminate, but they can still see colors. Just not all of them. So let's just come back to this figure. So for dichromacy, the M and L cone deficiencies are the most common. So deuteranopes and deuteranopsy and protanopsy. So these are the most common. So this means that most people who are colorblind have difficulty discriminating light waves in the middle to long end of the spectrum range. So this is going to be your blues and your greens. So for example, if you consider the wavelengths 560 nanometers and 610 nanometers. Okay, so let's so 560 and 610 nanometers. So neither one of these lights is going to activate the S cones very much. So if we come to about 560 here and 610 over here, so these two are not activating the short, the bluish cones very much. So neither one of these lights is going to activate the S cones very much. And the L cones, they fire at about the same rate for both of these, right? So let's look at the L cones. So here, so L cones here, and over here for the 510 be about here, right? So they fired about the same rate for both of these colors, but most of us can distinguish these lights on the basis of the M cone output. So the M cone output is going to be higher for the 560, be about right here. So the M cone is going to be higher for for the 560 than it would be for the 610, which would be down here. So if you have all three cones, you would label the colors of these two lights as being green and reddish orange. You know, so green for the 560, 610 for the reddish orange. Because with three cones, you have the response of the M cones, and that is going to be much different. So the response of the M cones is much different for a 560 nanometer light compared to a 610 nanometer light. So when you have that response from the M cones, that allows you to distinguish green from reddish orange. But because people with deuteranopy don't have those M cones, they can't make that distinction. So for people who have deuteranopy with no M cones, their photoreceptor output to these two lights is going to be identical because the rest of the visual system only knows what the photoreceptors tell it. And if a 560 nanometer light and a 610 nanometer light are making the having the same response rate, they're going to be perceived as the same color by a person with deuteranopy because they are missing the cone that would have the lower response to the 610 nanometer wavelength. So somebody with protanopy on the other side, so this is someone who has no L cones. Protanopy, this is someone who has no L cones. So they're going to have they will have a different set of color matches based on the outputs of their cone types, being they have the medium and the short wavelength cones. So these people would have an issue distinguishing between 500 and 600 nanometer light. So they're missing that high response to that 625. So they are missing this high response right here. They're missing that high response from the L cones. So this is where we run into problems with only two cones having that difference in relative activity of each cone. So tetranopy on the other side, these people, they're missing those S cones. And people with this condition, they have difficulty distinguishing with like blue and green, purple and red, yellow and pink, because they are missing the output of the S cones. Okay, so let's watch a video on how color blindness works. You can, we'll run through all this that we just talked about again, and also give you some visuals to go along with it.